Introduce our speaker, Daniele, for the afternoon session, and he will tell us about Yangians and W-algebras.
Okay, so 2 days ago, we spent quite a lot of efforts to show that we can find an element, which we had called the Lax operator, which essentially is an operator with coefficient in the W algebra. And these B minus and B plus are a space of lowest weight vector and highest weight vectors. So these have the same dimension, so let's identify them so that we can forget about this and just think that we are dealing with the square matrices. Okay, so why did we spend so much time in constructing this element? Well, because now we have infinitely many elements of the W algebra, and one of the main difficulty was that now not only they lie in the W algebras, but we provide an explicit realization as element of the universal enveloping algebra. That's what was actually the most difficult part. But we know the commutation relation in the universal enveloping algebra. So now today, let's try to answer this question. What is the commutator of this object? I mean, what are the commutation relations of all the elements of L? And so it turns out that I know the answer only in few cases. So if you know how to do it in general, it will be great. So positive answer, which I'll try to explain today, we need to fix the representation. So B minus and B plus are lowest weight vector and highest weight vector, some representation that we have denoted by B. So B is the standard representation. And of what algebra? Of a classical Lie algebra. So only in this case I know an answer. So it would be interesting if one can generalize to any Lie algebra, any nilpotent element, any representation. So let's say G is okay, we can include as a GLN without harm, but it's SLN or a symplectic or orthogonal Lie algebra. So these are the cases that I know how to compute this commutator. And what kind of relation do we get? We get some relation satisfied in some algebras of Yangian type. So what really we are going to prove is that there is a certain Yangian type algebra which maps in our W algebra in these particular cases. Okay, so this will be the outcome of the computation for today. And let me start with the simplest case for GLN. And I will just follow the exposition in Molev's book, which is a very good reference. So this Yangian of GLN, let's denote it by Yn. So is an associative algebra with countably many generators and also unit. So let's denote this generator by Tijr. So I and j runs from 1 to n, and r is greater or equal than 1. It's a positive integer, subject to some relations, which are as follows. So Tij r plus 1 commutator with Thks minus same commutator with 1 on the right. So this is equal to some quadratic expression, which is the following. So Thj s Tik r minus Thj r Tik s for every r and s greater or equal than 1, and we are assuming that greater or equal than 0, let's say, and we are assuming that Tij 0 is delta ij. Okay, so it's a bit involved, but let me try to give at least not motivation, but two observation just to justify why one should define this object, some kind of remark. So if you remember, in the first lecture, we introduced this matrix E, which contains in position ij, the element of the universal enveloping algebra, which represents the elementary matrix EJI. And there are some objects in the center of the universal enveloping algebra that we have computed, but there are also some other objects that can be computed. For example, the trace of e to the r belong to the center of the universal enveloping algebra. And I think are known as Gelfand invariants, maybe? Yeah, sorry, I'm not an expert in Yangians. I'm not quite sure if it's Gelfand or Steitzrin, but I hope no one will be upset if it's wrong with the name. So they should be known as Gelfand invariants. And this element, the entries of e to the r, they satisfy this relation. So the meaning is that if we replace Tij by the ij entry of e to the r, this identity star is satisfied. So I think one way to think about these Yangians was, okay, we have this identity in the universal enveloping algebra. Let's try to replace this object with some unknown variables, and let's see what kind of algebra do we generate. So I don't know if that's sufficient motivation to introduce this algebra, but this explain why there is this relation. Another fact comes from the formation theory, which was a little bit explained by Simone yesterday. So if we define the degree of Tij(r) to be r minus 1, then we have a grading. We can consider the associated filtration, and we can take the associated graded with respect to this filtration. So this is a universal enveloping algebra of the so-called current algebra of GLN. So just the polynomials with values in GLN. And as Simone explained, we can say that U, this is Yn, is a deformation of this U. Or another way to put this, as was remarked, if we rescale Tij(r) by some parameter which keeps track of the degree, so yes.
So the relations are non-homogeneous. Zero, right?
Yeah. With respect to this filtration, yeah, they're not homogeneous. Yeah. It's possible to define another filtration for which they become homogeneous. So there are two filtrations, like in the universal enveloping algebra, you can find two different filtrations: the polynomial one and the Kashdan grading.
Oh, so then, but so it's not a graded algebra.
No. So yeah, sorry. This is graded with respect to the filtration associated to this. So given a grading, we can construct a filtration, right?
Yeah, no, I mean, I was going to ask it before you mentioned the filtration. I was just asking whether it's.
Oh yeah, it's not
Yeah,
not graded. Yeah, not graded at all. Yeah, thank you. Yeah, in fact, we need to compute the associated graded, which is kind of very different object. And yeah, another way of seeing this. Okay, let's keep track of our filtration. So we rescale a little bit our object. We can define, let's say, this Yangian, not over C. Maybe I forgot to say. I should have written over C. So now we can define this over the space of formal power series. And equivalently, what Simone explained to us, this is the same as the following procedure. So we quotient by the ideal generated by setting H equal to 0. So this is U of GLN P. And if we set H equal to 1, we just recover our Yangian. And what happens? So the universal enveloping algebra of Lie algebra is off algebra. So these are the Yangian is also off algebra. So these are isomorphisms of algebras. So Yangians can be defined as homomorphism of as deformation in the category of algebras of universal enveloping algebra. So in the same spirit as quantum groups are constructed. And now let's try to rewrite these relations in a more suitable form for us. So the first thing that we will try to do is to remove the upper index, and then we will try to remove the lower index. So first we introduce Tij z. So we collect all the variables Tij(r) into a 1 power series, and then this is equivalent to the following identity. Okay, we have removed one parameter, so let's remove also the other indices. So now we take the generated series of all these Tij z, and we just be matrix. So how can we rewrite this equation, which is now become 2? Or maybe still 1 is equivalent also. We have seen this in the first lecture already. Sorry for writing it twice. Okay, let me remind what is this omega.
Daniele, these people are so much
Yeah, we will write this. And I will also explain the commutator, since I experienced it so far that was a very unlucky notation. So let me explain everything which appears in this formula, and hopefully it will be clear. So this omega we already met. It's just the flip operator. Actually, we can write it down explicitly since we have fixed, we are working over matrices. We are fixing up bases in some sense. And then, so what is the meaning of this commutator? So I just want to understand this as the generating series of all the commutation relation. So sorry for making it so nasty, but it's just the sum. So it's an element, formal power series in Z inverse and W inverse with coefficient in the Yangian. And then we have also some operator part. And as usual, I'm trying to avoid to write this tensor product sign. So I just assume that elements of the Yangian are coefficients. And so you pointed out that it's very bad notation. So let me just try to explain something done by physicists and other mathematicians smarter than me. So this is, what is it? So this is just P of Z tensor 1 times 1 tensor TW minus the opposite product. And usually this P of Z tensor 1 is denoted by T1 of Z. And 1 tensor TW is denoted by T2. It means that we are placing our T in position 1 or in position 2. So eventually the right way to write this commutator is T1 of Z, T2 of W. But it makes me so depressed that we are trying to do everything to avoid indices, and still we need to have the indices. So I just don't want to see indices. And I just remembered myself that this is just a generating series in some sense. And but the observation is that we cannot write this is equal to P of Z tensor T of W. But this is not, okay, because our algebra is non-commutative. Otherwise, of course, this commutator will be 0.
Should those t's in the commutator after the sum be little t's?
Oh, yes, thank you. Thanks a lot. Yeah, I don't know why I never used this feature. I started to use them. Thank you so much. Okay, yeah, I'm very sorry for misleading you several times with this bad notation. I hope it makes more sense now. Let's try to expand this identity. So expanding the last identity. So what do we get? Now it takes a few minutes, but one can compute all the terms. We get the following. So just to avoid any misunderstanding, I will use the clever notation rather than mine. Okay, let's denote by R of U this element, this endomorphism, in the tensor product of the endomorphism space with itself. And I should write one tensor R. So 1 is the identity in W. Sorry, I'm not going to do that. So let us assume the convention that whenever there is nothing, there is 1 in the space we are making computations. So this identity, you see, you can read it, is RTT. And in fact, it's called the RTT presentation for the Yangian. And what are the properties of R? So R is called an R matrix.
Sorry, I'm missing something a few steps back. If your T factors are on different tensor factors in the bottom left of the board, why does that not commute?
Because Y is not commutative. So the order which we multiply object matters. So we are multiplying endomorphism on the right and on the left, so there is no problem. But these are also coefficients which I'm trying to forget in the tensor sign.
Okay.
So they do not commute. Coefficients do not commute. And this R satisfies an equation which was already written in Dimitri's lecture. So this R satisfies the so-called Yang-Baxter equation. It's a solution of the Yang-Baxter equation. Okay, so let's write it down. And I hope these lower indices 1, 2, 1, 3, 2, 3 are clear after the Dimitri's explanation, which is just another way to rewrite this identity. Okay, for us, this RTT presentation will be much more useful. Are there other questions on this? Let me just say some properties of the Yangians that we will use. Okay, first I'll write some homomorphism. Let me start with some automorphism. So it's easy to see from this RTT presentation that if we multiply T1, by some element, by some, for example, let's multiply by Z to the K, then the RTT relation is satisfied. And of course, the inverse map is just multiplication by Z to the minus K. So this gives an automorphism of our Yangian, but more general, we may multiply by any, this could be substituted by any Laurent series. And now let's write some, okay, let me write another. So again, we may have a look at the RTT relation. So if we shift Z and W, nothing happens. So this gives rise to another automorphism of our Yangian. And then let me write an homomorphism that we are going to use. So let's say we want to send the Yangian of GLN to the Yangian of GLM by multiplying two matrices with coefficient in our base field C. Then if T satisfies the RTT relation, we multiply everything by A on the left and on the right by B. Then we get something that still satisfies the RTT relation, but it's in a different dimension, right? Because now it's a matrix which is of size M times M. So these allow us to construct a homomorphism from the Yangian, let's say, of size N to the Yangian of size M. Now let me write an anti-automorphism. Automorphism is just a homomorphism from the Yangian to the Yangian with opposite product. So how is this defined? We can map T to T inverse. So how to see this? Just multiply the RTT relation on the left and on the right by T1 inverse, T2 inverse. Cancel what you can cancel, and the result will be just the RTT relation, but you need to multiply using the opposite product. So this gives an anti-automorphism. And apart from part 2, and maybe part 1, which will come up later, so these properties that we have used, multiply on the left and on the right by some matrix, taking inverse, are exactly the operation that appears in this construction of L, in this quasi-determinant. So let's write a corollary of this. So these are very basic properties of Yangian. There are much more interesting automorphism and anti-automorphism, which you can have a look on Moller's book if you're interested. But these are just the one we need. So as a consequence, so let's assume that certain operator A satisfies the RTT relation for some Yangian, and that this quasi-determinant is defined, exists. And let's say that U and W have the same dimension M, then this quasi-determinant satisfies the RTT for Ym. And let's try to give a proof of this. It's just some simple observation now. We just need to remember. So let's start from the inner part. So this is the definition, and we are assuming it makes sense. So A satisfies the RTT for Yn, then A inverse satisfies the RTT for Yn with the opposite product. Okay, then this is our first step. Let's move. So we are multiplying on the left and on the right by some matrices. So this is an homomorphism. So this satisfies RTT relation for the same algebra. So Yn op, sorry, for maybe bigger, maybe smaller algebra, Ym op. And then we need to invert again. So we apply this anti-homomorphism. And then now we need to, our final result satisfies the RTT inverse for Ym op, which is Ym. So this is the general scheme that we want to use for W-algebras. And the main complication is that this quasi-determinant is not so easy. I mean, last time we spent a lot of time in proving the existence. But luckily, we show that the coefficients are in the universal enveloping algebra. So if we can show that the universal enveloping algebra, the Yangian are related, then we can just do this basic operation. So let me say that this is kind of the main idea that we would like to apply. And I will try to show a little bit how to do this, not in many details, but just to give some flavor. So I know it was quite a long trip to show the existence of the quasi-determinant, but once one can show this, we can construct a lot of elements in the W algebra, and also the relation comes almost for free. Okay, now the main observation is something which is very well known in the theory of Yangians and universal enveloping algebra. So if we take A of Z, which is now the following element, Z plus E. So this is a polynomial with coefficient in the universal enveloping algebra, and it's a matrix. This satisfies the RTT relation. And this is a computation which it's nice to check. What does it mean? Namely, so we have homomorphism from the Yangian to the universal enveloping algebra. And what does it mean that this satisfies the RTT relation? It means that if we replace T by A, the relation is satisfied. But A starts with Z, but it's not a problem because multiplying our T by Z is just an homomorphism, automorphism. So the map is given as follows. Or if you want more explicitly, then Pij R goes to delta R1 Ej. So this clearly shows that this is surjective. We are mapping onto all the generators of the universal enveloping algebra. And this is called the evaluation map. And just remind that this is the W algebra associated to the zero nilpotent. It's like the base case that we need to investigate. And now we want to apply this machinery to show that our operator L satisfies the same relation. L was defined as the quasi-determinant not of A, but of this A rho Z plus D. So there are a lot of things to check. Let me just write the definition. So now we would like to claim that we can apply some similar procedure to this and show that we can find the relation satisfied by this L. And one of the basic steps is the fact that here there is no A, but there is this A rho. But the most important part is that this coefficient still lies in the universal enveloping algebra. So up to some complication, let's say we can overcome all of these steps in our setting of finite W algebras. So we can apply the philosophy in this blackboard. We show that now our Lax operator satisfies the RTT for the Yangian of GLV minus, where V minus are the highest weight vectors of our representation. So I'm trying to, I won't give any detail, but the idea is just to use this basic property of the Yangians. And unfortunately, it's not actually using in a straightforward way. There are a lot of technicalities to check, but this is more or less how we want to proceed. Are there questions?
In all of this construction, that's what we were doing here, with all of the CN and it was all the GLN. It didn't seem like CN played very much of a role in it. If we did this for a different representation, what would where does all of this fall out?
Yeah, here. I don't know the evaluation map for different representation.
There are classifications for evaluation.
Yeah. I hope there are smarter representations to use. I mean, at the beginning, I tried to use the most natural was the adjoint representation, but it didn't work. Most natural, I mean, just because we can avoid talk about matrices and so on. Anyway, I hope there is a flavor of what's going on. I try to to pass to symplectic and orthogonal case. Let's see what can happen. So now what we want to do is the following. For orthogonal and symplectic, need to take a kind of more general presentation of the Yangian. And of course, it won't be the Yangian of GLN anymore. So it will be another object. Before that, maybe. Yeah, maybe I forgot. I mean, I think it's obvious, but it's better if I state this. So what does it mean that it satisfies our Lax operator satisfies the RTT presentation for the Yangian of GLB? We kind of generalize a little bit this evaluation map. So now we have a certain homomorphism from the Yangian of GLB, B minus, to the W algebra associated to GLN for arbitrary nilpotent. And these are the lowest weight vector of the standard representation. So this is the result, if you want. We can state like this. So there is no need to know anything about the presentation of Yangian and so on, just that we have constructed an associative algebra homomorphism. Let's try to construct a similar homomorphism where now here there will be SON or SPN. And yeah, we can choose GLN, but it works also for SLN. It's more or less the same. We need to mod out by some element in the center. Okay, so let me introduce this identity. Let's try if we can work out all the cases with one identity. So let's call this alpha beta gamma Yangian identity. So it's similar to the RTT relation, some term between T1 and T2 and T2 and T1. I think I choose minus gamma in my notes. I choose minus beta. Okay, let me stick to my notes, otherwise I state wrong results. Okay, let me try to explain this identity. So it depends on three complex numbers. So if alpha is 1 and beta is 0, then we are just multiplying the RTT relation by this polynomial z plus w plus gamma. So nothing changes. So gamma can be anything. So let's fix it to be 0. And this is exactly the RTT relation, RTT presentation for the Yangian of vector space B, GLB. Okay, so what happens now if beta is different from 0? So if beta is different from 0, there is this object omega dagger B. So I need to explain what it is. So if B is different from 0, we assume that on our vector space B, there is a non-degenerate bilinear form. And as you can imagine, it will be symmetric or skew-symmetric, since we want to deal with symmetric or symplectic algebras. And which is symmetric. So in this case, let's choose a number, epsilon, that we fix to be equal to 1, or skew-symmetric. In this case, we fix this number epsilon to be minus 1. So what happens when beta is different from 0? So if beta is different from 0, actually, let's take both alpha and beta equal to 1/2, and gamma equal to 0. So this gives the so-called RSRS presentation, which can be found in Moller's book, for the twisted Yangian. Actually, let me say extended twisted Yangian. And let me denote this by X. And this X depends on only algebra G. And what is G? So G is SON, as you may guess, if epsilon is equal to 1, or SPN if epsilon is minus 1. I mean, nothing astonishing. So I'm not going to talk about these twisted Yangians, but if you think about how SON and SPN are constructed starting from GLN, they are fixed point subalgebras. And similarly, these extended twisted Yangians are fixed point subalgebras of the usual Yangian. So just roughly speaking, not roughly speaking, I mean, it's true, but briefly. So we can define an automorphism of order 2, which I haven't defined in the Yangian. The fixed point of this automorphism will give rise to a certain subalgebra, which we call the extended twisted Yangian. And you may think that they are kind of similar to reductive Lie algebras. They contain a center. So these have a center C, and the quotient is called in Moller's book the twisted Yangian. And this occurs only in beta is different from 0. Okay, so G is always SON, SPN. we can just add a relation to that identity to mod out this kernel, but let's don't do that. Just let's stick to the most simple case. So instead of working with twisted, I will just work with extended. So now we would like to play the same game. And it was good that David pointed out. So the first thing that we need to do is find an evaluation map to the twisted Yangian, use the machinery, which unfortunately I just erased, and show that our Lax operator satisfies the same relation given by the evaluation map. So if we can do this, we found all the relations, and we have construct similar homomorphisms, not from the Yangian of GLN, but from the twisted, extended twisted Yangian. Sorry, other question at this point. Okay, I hope the machinery is clear. But in order to do, yes, please.
What is it? RS. You can change T, you don't change the R. You change T to S.
Yeah, because I think it comes from the following fact. So this is R, an R matrix, and now this is a kind of new R matrix S, and they satisfy a relation which is called RS. This is a kind of by the way, I mentioned it, but I haven't explained what is this omega dagger. So omega dagger is the adjoint on the second factor. Adjoint of omega on the second. Omega belongs to NV tensor NV, we take the adjoint on the second factor. So it's obtained from R via some adjoint, so it's kind of related to R matrices.
In both cases that you presented, the gamma is 0. So
Yeah, this was something.
Non-zero gammas that should be element somewhere.
Yeah, I want now it will appear in W-algebras. That's why I want to keep gamma. Then thanks a lot for asking. But we can always assume gamma is 0. Now I want to state few properties similar to the one we state for the Yangian. And then we can get. So if we set gamma equal to 0 as in Molle's book, the center has a very nasty equation. So, I mean, not nasty, it's just that I always forget that. That's why I think it's nasty. But if we set gamma different from 0, it's very easy to write down. We need to mod out by this ideal, which really shows that we are quotiented by something which is similar to how we define SON or SPN. But I mean, it's just some details I'm very interested. But I think this relation really explains that we are working with symplectic and orthogonal Lie algebras. In Molle's book, there are 3 terms occurring. But I guess if he kept gamma equal to 0, he has very good reasons.
Right, this is that related to the center or related to the fixed?
Yeah. If we impose this relation plus this relation, we are already modding out the center. Yeah. So in order to get twisted, we need to have 1 plus 2. If we choose some particular values of this gamma. Let's now try to write some properties similar to homomorphism, anti-automorphism of Yangians that we wrote. So assume element in some algebra, which is some endomorphism subvector space, satisfies this alpha beta gamma identity. So let's write just few things that we need. So the first one is why we can always assume gamma equal to 0. So what happens if we apply an affine transformation? Actually, if we just shift Z, then we can remove gamma. So this explains why it's a little bit inessential, but let's keep it for the moment. And then I'm not sure I remember everything. So what happens if we multiply on the left and on the right by 2 matrices? Let's already denote by IW, IU, since this we are going to use. So if you remember, it was a homomorphism. So we should expect that these values of alpha beta don't change. And that's the case. But what changes now is the target space. So the representation is different. So it satisfies this identity for a different V. If we get the same V, then we get an automorphism. And then what to do? We need invertibility.
In the second line, you have replaced AZ by AZ plus B, or?
Yeah, sorry, this is,
okay.
AZ goes to this, AZ goes to
okay.
this. Yeah, thanks
Thank
a lot
you.
for pointing out. What happens to A inverse is satisfy the same identity for the opposite product. And now you may easily guess that the opposite product is obtained just changing alpha and minus alpha and beta and minus beta. And we need to keep track of gamma, which I never remember. So that's why we need gamma, because it appears quite naturally for W-algebras. And then now we can apply the same procedure to understand what kind of relation is satisfied by the quasi-determinant. And as before, we invert, so we are changing sign to alpha and beta. We are multiplied by matrices, alpha and beta don't change. And then we need to invert again. So alpha and beta now comes to the original position. And let me write gamma. So, okay, some properties, just to say that if now we can show that our matrix A in our universal enveloping algebra satisfies some identity of that type for some values of alpha, beta, and gamma, then we can understand what kind of identity is satisfied by the operator L.
The last line of those dimensions that you have.
Oh, dimension of U, thanks. I wrote U. I will check and let you know.
I think it's dimension of V because you first invert AZ in V, and after you take the quasi-determinant to go in U and W, which are of the same dimension. So it's V and U, or V and W.
Yeah, for W-algebras, we are lucky that they have the same dimension. I will check it. I think it's the vector space from which we apply our quasi-determinant.
If we put W instead of V, it makes 0, so there is nothing if we...
Ah, you say V instead of... yeah, that's B and this is U. So B comes from first invert, so we always invert. Sorry, yeah. Let me write that. Anyway, it's a number that we can set to 0, luckily. So if we believe that we can apply all the machinery developed before, even if we are not working with A when inverting, but with this A row, then we can get an answer. So now the only question is to find this evaluation map, the analog of the evaluation map in this alpha, beta, gamma case. And yeah, let's write it explicitly. Let me write the right coefficient of gamma. Okay, so now we take this that we always need to think as the kind of an ancestor Lax operator, or if you want the Lax operator for the zero nilpotent element. Let's try to see what kind of relation does it satisfy. Just remind, this is the Casimir of the representation. And B is the standard representation. G is SLN. It's type A, B, C, D, basically. Okay, that's the only thing that I know how to do. And then it satisfies the alpha, beta, gamma identity, Yangian identity. According to the following, we can write a table. One case was already studied. So if alpha is 1, beta is 0, and gamma is an essential, let's say it's also 0, this is what I try to motivate at the beginning. So it's GLN, SLN. And I remind you, this is the RTT relation. And then if beta is different from 1/2, and there is the following value. Maybe now I appreciate why Molev put gamma equal to 0. So gamma actually was easy to remember. It was epsilon over 2 if G is SON or SPN. And according to this first property, we can always rescale in order to have some evaluation map with the, but in order to have that this A satisfies the RS-RS relation. So this was just a way to cover all the two cases. Yeah, basically two cases. And actually when beta is, so in the second case, I mean, I already have discussed the first case. So in this case, we get a homomorphism. And this is also called the evaluation map from the extended twisted Yangian to the universal enveloping algebra. So now let's try to replace this universal enveloping algebra, which is kind of our basic case, to an arbitrary nilpotent. And maybe I can say the proposition is that now this L of Z, the Lax operator, I remind you, is this operator, modulo a lot of difficulty, but the strategy is always the same. Try to use these three properties, starting from the fact that our operator for the simplest case, for the W algebra when F is equal to 0, satisfying a certain alpha, beta, gamma identity. So this operator satisfies, so is the identity, and so This is already discussed, the case alpha equal 1, beta equal gamma equal 0 for GLN, SLN. And this means that, as already wrote, we have constructed an homomorphism. And now the next case will come with alpha and beta is different from 0. And gamma now should be read from here and from this original value. So if I haven't made mistakes, it should be the following. But anyway, I'm going to write, but it is an essential, since we can always set to 0. So what do we get? We found the homomorphism from this extended Yangian of certain Lie algebra, let me say G bar, to the W algebra. And what is G bar? So G bar again is just symplectic or orthogonal algebra now on the space of our lowest weight vector. And depending on the parity of the restriction of the bilinear form on V to the bilinear form over the space of highest or lowest weight vector. Okay, so that's it. Yeah, that's a good point. No, but it's for rectangular nilpotent is surjective. For it's not surjective, but in an explicit example, I want to show how to tweak it to make surjective and getting all the possible generators and all the possible relations of the W algebra. Yeah, thanks. It's not at all.
Thank you. So Vidas is asking about the third line. There's a gamma minus ZB. He doesn't understand why there's a B in the third line.
Third line of what? Blackboard?
Yeah, sorry, this was from a few minutes ago, but he says it's on that board that you're holding.
Oh, maybe
On the third line there. How does the gamma get a B?
I think it's 2B.
2B?
Yeah.
Okay, so can you explain the origin
Actually,
of
it's
that B
plus 2B,
correction?
sorry.
All
Plus
right.
2B, but I mean, it's not important.
So why is there a shift in gamma? Can you explain that? Or do you just have to do the calculation?
No, I just hope I haven't erased the black. Yeah. You see, because if we shift Z and W, nothing happens in R because we have Z minus W. If we shift Z and W, then gamma takes something from Z, something from W, so it becomes 2B. And here also I think it's 2B. No, that's correct.
Does that answer your question, Vidas? Okay, we may
Yeah,
have lost him.
2B. Yeah, it's just the same. Yeah, maybe this can be checked directly from this, as we did for the RTT. These properties can be checked directly.
Okay, he says he's good now.
Okay.
Excellent.
Other comments or questions? Okay, if not, let's thank Daniel again.